So welcome to my talk. I'd like to talk about next generation blackholing to counter DDoS attacks. So this is actually the full title. My name is Chris, or actually Christoph Dietzel, and I go by Chris. And this is joint work with Matthias, Georgios, and Anya. So as many in this room face the issue of DDoS attacks, right? And particularly, we're speaking about volumetric DDoS attacks. And I just put the records observed and publicly reported by media, peak traffic of DDoS attacks within the past 4 years on this slide. And we see in 2015, back then, it was like 200 gigabits. I digged up the news and media reports about it. It was a big thing. It's like 200 gigabits. Oh hell, what can we do? What's happening? And just a year later, we had a new record of 1 terabit per second peak, and then 1.7, so new record again, and it was always big in the media. And we know this is a growing issue. However, it's not only really the peaks and the publicly reported ones, but actually we're facing a lot of attacks in our daily businesses, right? Like on a weekly basis, nowadays, 100 gigabits, 10 gigabits, 50 gigabits. So also a high frequency of a lot smaller ones. And since this is not an entirely new topic, there is an ISP DDoS defense toolbox. So we have tools to defend those DDoS attacks, to mitigate them or to get around them. One actually fairly old way to do it is by using ACLs. So I don't know what's going on with the slides. So actually it allows arbitrary granularity of filters. But the issue is it's a bit vendor specific because each vendor implements those in a different way. And since the implementation is different, the configuration is different, and the scalability is different. So if you come from Nokia and go to Cisco, you cannot just assume that it works the same way, in particular with scalability at the edges, so if you use it really a lot. And it's a per device configuration in most cases. If you use configuration proxies and automated systems, that's not entirely true, but in general, if you're a network operator, you need to configure those on a per device, in best case, semi-automated way. So traffic scrubbing services became way more popular over the past years. So this is actually the carefree service, the carefree product. So if you're hit by a DDoS attack, you go to a traffic scrubbing service, they will clean your traffic and redirect it towards you. This is usually done with BGP. There are on-demand and always-on kinds of products. Always-on means they basically are sort of your CDN and hosting your stuff versus the on-demand where they're really using BGP, redirect the traffic, clean it, and send it back to you. So over the past years, we saw a standardization and implementation of BGP flow spec. This is within BGP, so it's a feature of BGP basically, and it allows to configure rules at neighbor networks. So meaning I can configure rules on the device through BGP at my peer's router. And traffic can be discarded at 1 hop away at my neighbor's router already. Filters are allowed at arbitrary granularity, and cooperation is required because I cannot simply use it. My neighbor has to activate it and has to allow me to really use this feature. So it requires the cooperation in a sense. The good old remote triggered blackholing or blackholing is a very easy and straightforward way of BGP or using BGP to configure rules at another neighbor network. In contrast to FlowSpec, which is also BGP based, it does not allow filters on arbitrary granularity. Actually, it just allows filters on IP granularity, meaning traffic towards IP can be discarded. So in best case, IP or IP prefix. And it also requires cooperation. Not as direct as in the sense of FlowSpec, but the neighbor has to adjust its configuration to accept /32 blackholing announcements and to be honored then. So now we know there is a toolbox of more or less good defense tools. But if we're asking how would we actually do DDoS defense at IXPs as of today? So we know all those tools and we know the limitations, but also with which advantages they're actually coming. So our idea is, let's combine the good properties of the existing solutions and eradicate the current shortcomings. And another plus is we can do this at the IXP. And the IXP, as of now, offers services to 100 of ASs at the same time, meaning they don't have to connect to a new network or have a new contract or have a new setup. It just works within the environment of the IXP, or should work in the environment of an IXP. And IXPs have, as of today, multiple of terabits capacity, spare capacity, right? So the capacity to absorb large DDoS attacks is in place already. And IXPs are also a trusted part of the interconnection and internet community already. So if you continue to think about it, we first need to recap quickly, what does blackholing actually do today? I assume that most in the room know what it is and how it works, so I just quickly recap what's going on. So on the left-hand side, you can see the control plane picture. On the right-hand side is the data plane picture. And what actually happens on the control plane is there's an IXP, and to the IXP we see 3 ASs connected, AS1, 2, and 3. And AS1 is hosting a service behind the dedicated IP address. It announces a /24 towards the route server, and the route server propagates the announcement towards AS2 and 3. So both ASs can reach AS1. So in the next step, we focus on the data plane, and actually it's the same setup, and there are users sending traffic from AS2 and 3 towards the service and consuming it. Now let's just assume there's an attacker using an NTP reflection amplification attack, and traffic is coming over the 2 ASs, AS2 and AS3, across the IXP towards the service of AS1. And the issue here is that it's a DDoS attack, and it's consuming more resources than actually available. And as a result, either the IXP port, the internal network, or the service just goes down. So we have a denial of service here. And next step is for the to mitigate it with the IXP-based blackholing. A simple change. We just change or add another announcement, just the IP address of the service with a community to blackhole the traffic. AS1 can just send it towards the route server, and the route server itself is propagating it again, like same scenario. However, in this case, since it's a /32, it is not guaranteed that it's actually accepted. So in this toy example, actually, AS2 is only accepting it, meaning honoring it, and AS3 does not. So the effect on the data plane is that the traffic is discarded, but just the traffic from AS2, right? So ingress IXP, it is discarded, and traffic from AS3, attack traffic, is still getting through. And for the users in AS2, they can't really reach the service anymore, so it's sort of supported the denial of service. And AS3, it's unclear, and it's not predictable what's actually going on. In some instances, customers report, okay, it's really helping us, and they can still consume the service. In other instances, they still are under denial of service. So let's focus a bit on those limitations which are very obvious. So actually, blocks the IXP-based blackholing blocks unwanted and wanted traffic at the same time, right, in the instance of AS2. So it doesn't discriminate, it just blocks all the traffic towards this /32. And it's hard to predict behavior because we don't know beforehand who is going to honor the /32 and who is not. Even if we would know, we don't know beforehand from which networks the attacks coming into our network, right? So it's just hard to predict, and we can't really count on it. And the last thing is, on a subset of peerings, as a result, it has just no effect. So the benign traffic is still going through, but also the attack traffic. So we don't experience this. And to really understand the limitations of the blackholing and how we would need to design a new system, we dig a bit deeper into those limitations. So on this slide, we just did a measurement analysis on a DDoS attack that happened at the IXP. We are looking in this plot at relative traffic shares of a 40 gigabit Ethernet IXP port from one member and the ingress traffic, or the traffic that goes towards this customer. And we see that at 20 past 20, it happens that there is a memcached attack on port 11 to 11. This is the red part of the plot. And we see before this attack happens, actually, it's mostly web traffic. And then with the beginning of the attack, the distribution significantly changes, and we see a lot of attack traffic red. However, we still see a significant share of web traffic, about 30%. And if we use blackholing in this instance, and as happened in this instance, actually all the traffic is discarded. So as a result, we have some sort of collateral damage, because actually the 30% of the traffic would still be there, and it's still benign traffic. So the next limitation we're focusing a bit is blackholing is an all or nothing approach. So it has prefix granularity, so drop it or don't drop it. And actually, you can do a per peer selection, not discarding traffic from all your neighbors, but you can select subsets at an IXP. However, it's still very, very coarse-grained. So for this, we did a measurement analysis on the black hole traffic at the IXP over a week and just looked what traffic actually gets black holed at an IXP. And we compared it with the regular traffic we observe. And we see that those are the most common amplification attack protocols, right? So it's NTP, it's LDAP, it's memcached, it's all this stuff. And we see that compared to the benign traffic, it's a very significant share. So actually, the conclusion here is we just need more granularity. So for the final measurement study we did, we actually wanted to see from a user perspective, how does blackholing behave? So how ineffective can it be? So what happens if not everyone is honoring our blackholing announcement? And therefore, we went to a booter service and bought a DDoS attack towards our servers and our AS. And we bought it, and then we launched the attack. We ran it for 10 minutes, and it was an NTP attack. And we just did it over the multilateral peering at the IXP. So no bilateral peering, just a multilateral peering at the IXP route server. And 10-minute attack to a /32 prefix. And then we, after half of the attack, we activated blackholing. And actually, we see in the first place that traffic came in from about 40 peers, right? So the blue dots in the white part of the plot. And then traffic levels between 600 and 800 megabits per second. And then the gray part is actually when we activated blackholing. And the result is, in this case, well, it does not really discard a very significant share of traffic, right? It reduces by, let's say, 100 megabits, maybe 200 megabits, and it's coming from a smaller number of peers, just 26. But what we are seeing here is a good chunk of the peers that's sending the DDoS traffic, ignoring the blackholing request by not honoring the /32 announcement from our AS. And the conclusion here is the signaling is too complex. So if we always need to involve everyone at the IXP, it's just too hard to make a significant impact. So actually, the requirements for an advanced blackholing are we need better granularity. So fine-grained filtering, source, destination, header fields, arbitrary fields. So source IP, destination IP, okay, but even more detailed, like UDP, TCP, or the layer 4 transport ports. So we need reduced signaling complexity. So it should be easy to use, short setup times. It should feel like the blackholing we are using today. So we don't want to change the systems, invent a very huge API or something along these lines. And the level of cooperation should be lowered. So we don't want to involve any parties at the IXP, as proven by the remote triggered blackholing might be ineffective. So we want to have telemetry. So we really want to know at any point in time what's going on. As from a customer perspective, I want to see how much traffic is discarded and to which filters or to, actually which part on which filter is discarded at the IX. And we want to have scalability, right? So we just don't want to have it for small attacks or the super big ones. We want to have the same performance, the same number of filters. We want to have a short reaction time and actually no complex configuration. And if possible, we want to meet all the above requirements with a minimal invest. So we don't want to buy traffic scrubbing boxes or invent new services or invest in new infrastructure. And actually, the idea or the proposal we have is fairly simple, but effective. So the same scenario from before. And again, /32 announced from AS1 towards the route server. But encoded in the BGP community is a reference to a very specifically defined filter. And in the case of the NTP attack, it's just, please drop all traffic towards the IP of my service that has the NTP port. And this signal goes from the route server directly to the data plane, so not involving the other parties. And on the data plane, it's just checked according to the usual filters, whether it's a valid announcement or not, but then it is accepted and it's just implemented in the data plane. So we instantiate filters on our platform, and as a result, actually the traffic is, in every case, blackholed. We can not only blackhole traffic, we can also rate limit traffic and say just NTP traffic 100 megs or whatever, so that we have really this sufficient arbitrarity in this case. How our system looks, I just give a overview of the different layers. So first we have the signaling layer, and our thinking is, yeah, let's just use BGP. We don't need to really change how the system interacts with customers as of today, and therefore just encode a mapping to a set of filters, which can be defined by customers or predefined filters or whatever is the easiest. We could also think about an API, obviously, which comes with advantages in the authorization, whether you're authorized to discard the traffic towards your prefix IP or towards you. And yeah, it goes into an IXP interface, which validates all this stuff. And then we have a blackholing manager, which actually needs to always have the set of rules actually should be represented in the platform, and also abstracting from the implementation. Because as I mentioned before, some of the ACL stuff on the routers is different from vendor to vendor. And if we have an abstraction layer, we can do it on different systems basically at the same time through the same interface. And yeah, then we have actually a filtering layer which happens on the data plane within the boxes. And here we just zoom at the management and signaling part. So actually what we're doing is we have an iBGP session with our blackholing controller, like from the route server, and then we pass the BGP messages, simple so far, and then we process those and check them with the routing information base, just to verify whether someone is not allowed or is allowed to announce those. And then we just check the configuration changes or take the configuration changes and only the delta, the changes, and process them. We need a maximum burst size token bucket queue so that we can yeah, shape sort of like if someone is announcing a lot of filters, a lot of rules, we should implement to smoothen it a bit and yeah, not going into the trouble of overloading the system. And then we have the network manager, which actually is the abstraction of the implementation. And our suggestion is here a coarse network manager, SDN network manager. It really depends on the hardware of the IXP, which hardware is deployed, and actually the implementation can be done in different ways. So actually, now we have all the building blocks. So we have the granularity. We allow filtering on UDP, TCP, the different ports there. We have a very low signaling complexity, meaning that we don't need the cooperation of the others, and we just have a BGP community or maybe an API to really interact with the IXP. So only interact with the IXP, rest is done in data plane. And yeah, it's enforced by the IXP thereby. We have the telemetry, we have a monitoring system with the statistics you would need to understand what's actually going on. We have the scalability, so we're dropping the stuff in line rate in the actual fabric, and we implement it in the existing hardware at the IXP, so no new equipment needed. And our implementation challenge are mostly that the BGP processing part is not trivial. If we look at the updates, withdrawn, what happens if there is a withdrawn, and to keep the states, if you want to have like multiple, or you're having multiple route servers, but you just want to have one state and all this stuff, and the configuration proxy, which is hardware vendor specific, but this happened to be another machinery or system in our system, and this increases complexity significantly. So the issue is we're not configuring the boxes because we do it on sub-second time frames, so it has to be done through a proxy and through a system. And actually, what we have in place was not really 100% designed for configuration changes in sub-second granularity. And yeah, the question is a bit, why not really using, or why not simply using FlowSpec? Yeah, the issue here is, first of all, not all vendors fully support it yet. And actually, the real reason for us at IXP is that our route server software does not support it, but we implement it in a ways, if the route server would be able to export the FlowSpec rules in a generic format, we could also take it in the rest of our system. Since we build those different layers, we can just change this part, and the rest of the system may remain the same. So now the burning question, does it scale? So actually, we have two relevant dimensions for scaling. So scaling with the numbers of filters and IXP ports, where those filters should be applied. And we have configuration update frequency, right? So new blackholing request or filter request, actually. And the first one, yeah, we need just a sufficient TCAM space to really match the header fields and really do it with a lot of rules for a lot of ports. And we did a measurement in the lab with our gear to really figure this out. I have the results on the next slide. And the other thing is really do sort of a black box test, like throwing the filtering rules in on one side and waiting how long does it take to really apply in the data plane. So when is the traffic discarded? And we have, as the prototype or the system design stands, we have allow 4.3 filter updates per second on average, and 70% of the updates, blackholing updates, are below 1 second. So going back to the scalability of the system, so what I have here is I have the MAC filter criteria, means filters applied on a MAC address, like MAC filters, and on the other dimension I have the level 3 and level 4 filter criteria to really then drop the traffic. And this is the assumption that under a given n, and n is defined as set of configurations we observe at the IXP as of today. I can't, due to NDA stuff, not go into more details here. But if we assume that 20% of the customers at the exchange is using it, it scales pretty well, right? Like 10 times n on the y-axis and 4 times n on the x-axis. However, if we increase slightly the number of IXP members using this system, we don't really scale that well anymore. We just have, from what we observe today, 8 times more, and the other criteria 3 times more. And if every member at the IXP would actually use the system, the scalability, yeah, is still lower, but given that it's not a realistic scenario, as about 20% today using remote triggered blackholing at the IXP. So we just did our measurement experiment again. So we ordered another DDoS attack onto our new system. We announced the /32, and this time not only to black hole the traffic, but first we did a shaping on 200 megabits. And yeah, this is basically the result. So it instantly worked. First we shaped the traffic, then we dropped the traffic, and no cooperation of other peers is allowed. So for the shaping part, the number of peers that's sending traffic remains stable. And for the dropping part, traffic really goes to 0. So and we just filter on NTP traffic, right? So if we would have a real service, this would still be reachable and there would be no effect from the DDoS attack on it. So in summary, a number of DDoS mitigation solutions exist today, but most of them have scalability issues or are fairly expensive. So we identified and measure blackholing limitations, so we really got a good understanding of what does not work, what works, and why does it not work. And we propose a new blackholing system, just call it advanced blackholing, and try to combine the benefits of what's existing there and merge it into one system at the IXP. And yeah, our prototype works very well and has a BGP interface, so you just need a BGP community, or you could work with the API interface. And we evaluated our system and actually figured that it proved a good scalability here. So that's it content-wise now from my side. I just have one final remark. DE-CIX New York peering LAN renumbering. So if you didn't change, do that. Please, cutoff date 28th of February. After that, we are blocking BGP ports with our new system. Okay, so that's it from my side. So all the details, if you're curious what we did and some more experiments we did, can be found in this paper. Thank you.
Hello. Hi, Avi Friedman with Kentic. I have a couple questions just to understand what's going on. So is the policy being abstracted and then sent to people to apply on their end, or is this being applied at the exchange equipment?
It's applied at the exchange equipment.
Okay. And then the second question, what's the authentication to make sure that people don't try to push policy for things that are not under attack or affect other people?
Yeah, so it's like with the normal blackholing as well. So for an API, you log in a customer portal or authentication towards an API, and with the BGP, it's just like IRR databases and filters there, as we apply those today at the route server as well.
Okay, so it's going through filters for the person.
Yeah.
But I could still say that someone else is attacking me, but then it would only apply to me, or would it apply to all the peers that are?
So if someone attacking you, so actually it just works by design for your IP prefixes. So you may not announce a prefix, you can announce your prefix if you're under attack, and it's just propagated toward the IXP, and the traffic coming from all our ASs is dropped ingress at the IXP fabric.
Okay, so if someone is attacking me, I can't cause that to be source. Okay, got it.
Exactly.
Thank you.
You're welcome.
Quick question, Brian Dixon, I'm with GoDaddy over here.
Sorry.
You're doing all the validation based on IRRs. What I'm wondering about is, would it be feasible, possible, do you have all the information you need to do BCP 38 source filtering for all of the members? Please.
Yeah, I see where you're going, yeah.
Because I think most of the black hole necessity comes out of spoof, or I mean, a significant amount. So preventing the traffic from being multiplied in the first place is going to be much more of a win, I think.
Yeah, two things. So I agree with you. So the root cause of DDoS is spoofing. And the second remark is actually we still don't want to, so we want to stay as much neutral as we can. So basically, if you are saying drop my traffic to my IP, that's fine, but we don't want to interfere with what's going on in the internet and just force people to
not spoof?
To not spoof, yeah, correct. But the question would be, why is spoof traffic within the ASs? So if you would apply filters, if we would build such an anti-spoofy filter and you would apply it, like you would decide you want to do it, that's a different story then.
Right, but that's the problem, is nobody's doing it. This would provide at least a mechanism for everybody to sign up to it, scalably. All you have to do is make it a checkbox, and then make that checkbox mandatory if you want to join the IX.
Yeah, but I don't know. It feels a bit like I'd be the internet police then, but it's a fair remark.
Rüdiger Volk, Deutsche Telekom.
Hi.
I'm not going to deeply discuss the authorization thing, but I think your statement that, well, okay, just use the usual authentication for BGP is a well-defined technique that can be relied on. Aside from the question of a dependable authorization scheme that I really would like to see, I think you may be missing one interesting function that should come with this. You are changing your simple layer 2 switching fabric to something that is doing some magic. Some traffic, and actually hard to characterize if you don't have insight of what the logic is disappearing. Wouldn't you need to actually expose to the members of the exchange the current status of what traffic you are blocking?
Yeah, so actually the idea is that we provide those insights. So we need to...
Yeah, well, okay. Probably should go into the presentation as well. And then actually also an interesting second level question comes up. What is the implied dangers of actually making that information available? Probably needs to be looked at. I'm not sure whether it really is a danger, but just publishing critical security information should not be done without. But
yeah, not publicly, Rüdiger. You can log in Deutsche Telekom, and then you'll just see the relevant statistics.
Hi, Roland Dobbins, Arbor NetScout, or NetScout Arbor, I'm not sure what I'm supposed to say these days. So I just want to make sure that I can disambiguate a little bit of the terminology that's being used here. If I understand the way the system works correctly, is you have predefined schema, BGP community, and attributes you share with your IXP participants, and so they'll advertise a destination IP address, and they'll use communities and attributes to describe the layer 4 characteristics that they want to drop, and they send that advertisement to your route server with BGP. Then your route server talks to some kind of orchestration system that then goes and it uses what? Quas, it uses ACLs, yes to both, I guess.
Yeah, so actually, as I said, it's a prototype, so the initial idea is to just have this mapping you just were explaining. But in the future, you can also say, okay, maybe we just want to have it purely dynamic. So you log in a customer portal, you define your rules there, and then you reference those. So it's not a publicly available list, but a custom list for each member.
Sure. Yeah, I understand. What technology is dropping the packets? Is it Quas or is it ACLs or both? What feature is dropping the traffic?
Okay, yeah. So it's in this vendor type it's Quas, but actually it does not really matter because we looked at different vendors, and for different vendors, different technologies work differently.
I understand you guys are out of the way. Okay, so I guess my question is, I was very, very confused by the title of this presentation, because when we're talking about DDoS mitigation, blackholing has a very specific meaning.
Yeah.
Right, destination-based blackholing, source-based remote trigger blackholing. What you've really built here is a DDoS, attack mitigation system where you've abstracted away the underlying packet forwarding or dropping technology, right? You have a system that is essentially technology independent, right? And so I would just suggest that for the sake of clarity that you don't call it blackholing, you call it something else. But it's very cool, and thanks for describing it.
Yeah, good, fair point, yeah. So it was, so my challenge was, my challenge was, if I speak about something different, nobody really knows what this talk is about. If I refer to blackholing, everyone knows a bit in which direction I'm going, but it's a fair point.
Yeah, that they know what it actually isn't.
Yeah, fair enough, yeah.
So, okay. Ace Kamari, Google. One of your slides had a pretty graph in showing the traffic broken down by port from a customer. Do you generally collect that?
No.
Okay, I didn't think so. I just wanted to make complete.
Thank you.